This is Unit 3, Thermochemistry. And thermochemistry is the study of relationships between chemical reactions and the energy changes that involve heat. So Lesson 12 is going to focus on energy and enthalpy. Now, remember back to 8th grade, for physics, energy is the capacity to do work or to transfer heat. And there's two types of energy that you've primarily studied. The first is potential energy. And potential energy, remember, is stored energy. It's energy that's based on position. And the opposite of potential energy is kinetic energy, which is energy of motion. So it's produced by a moving object. And you might have learned in physics that kinetic energy is equal to 1/2 the mass times the velocity squared. Well, in this class, we're going to focus on two additional types of energy, which are really just subgroups of potential and kinetic. So chemical energy is a type of potential energy. It's energy that's stored within chemical substances. And thermal energy is a type of kinetic energy because it's the energy that's generated from the motions of atoms. So the law of conservation of energy states that the total quantity of energy in the universe is always constant. Energy can neither be created nor destroyed. So here's just a picture of potential energy versus kinetic energy. When the biker is at the top of the hill, the biker has a lot of potential energy, the potential for motion, okay? And as the biker goes over the hill and down, he gains motion, and so he gains kinetic energy. Now the units for energy are joules or kilojoules, and what you're used to seeing is actually calories, like the energy content in the foods that you eat. So 1 calorie is actually equal to 4.184 joules. Now in physics, you might have used kilograms meters squared per second squared, but we're not going to use that unit in chemistry. Now, in thermodynamics and thermochemistry, there's two things that we look at. The first part is the system. So the system is the part of the universe that we're studying. So, for example, if you're doing a reaction in a beaker, the beaker would be the system, everything that's included in that beaker. Everything else we call the surroundings. So, we can have an open system, which means that you can exchange mass and energy into the system, okay? And usually that's in the form of heat, this energy change. And the open system is exchanging that mass and energy with its surroundings. You can also have a closed system, okay? A closed system only allows the transfer of energy as heat, but you cannot change the mass. So for example, here's a piston. A piston is a closed system because the gases inside cannot escape. However, it can transfer energy through conduction in the sides of this piston. So an isolated system does not allow the transfer of either mass or energy with its surroundings. It's completely closed off. Now, there's two ways that energy can be transferred. The first is work, okay? And work requires a force. So a force, remember, is a push or pull on an object. And work is the energy that's being transferred when a force moves an object through a distance. So the formula for work is work equals force times distance, because you need to move some object using a force through a distance. The second way that energy can be transferred is in the form of heat, which we give the symbol Q in chemistry. So Q is the symbol for heat. And heat is when energy is being transferred from a hotter object to a colder one. So, the definition of thermodynamics is the study of energy and its transformations. So this unit is going to focus all on energy and the transformation of energy through chemical reactions. The first law of thermodynamics says that energy can neither be created or destroyed. You can convert energy from one form to another, for example, potential energy to kinetic energy, or solar energy to electrical energy, but you can't create or destroy new energy. The energy of the universe is constant. So, we call this internal energy of a system E, the sum of all the kinetic and potential energies of the system. And this change in energy that we're going to be studying in chemical reactions depends on both heat, Q, and work, W. So if we want to monitor the change in energy, remember energy can only be transferred two ways, through heat or through work. So if we're finding the change in energy, the sum of the heat exchange between the system and the surroundings, we are going to have to take into account both Q and W. Now, the signs of Q and W are really important. So if the system is doing work on the surroundings, meaning it's doing work, it's putting out work, you're going to make work negative. If work is being done on the system by the surroundings, work is positive. If you are gaining heat by the system, so heat is coming from the surroundings into the system, then your Q, your heat, is going to be positive. But if you're losing heat, if the system is losing heat to the surroundings, your Q will be negative. And then finally, if energy is being gained by the system, that means your change in energy is going up. So it's positive. And if you're losing energy, if your system is losing energy, you will have a negative delta E. Now, gases can also do work. So when work is being done by gases, there's a special name for this. This is called pressure volume work. And the work being done is because the gas is either expanding or compressing. So the work done by a gas on its surroundings, W, is always going to be equal to the negative pressure of the gas times the change in volume of the gas. So whether it's expanding or compressing, you're going to take the change in volume. And remember, anytime you have a change, for example, change in volume, change in temperature, change in mass, it's always going to be the final minus the initial. So the change in volume will be the final volume minus the initial volume. So here's an example of a piston. So pistons contain gases in them, and you can see that initially the gas is squished way down here, but as the gas expands, it pushes the piston up, okay? And so the pressure not only changes, but the volume will also change. So this gas is doing work because it's changing the pressure and it's changing the volume. Okay, so let's do some example problems for calculating the change in internal energy. So in problem number 1, they give you Q and they give you W, and we know that delta E is equal to Q plus W. So all we have to do is plug in 0.763 kilojoules for Q and negative 840 kilojoules for W, and we'll get the total change in internal energy, which comes out to be negative 839.237 kilojoules. Alright, let's take a look at number 2. A system releases 66.2 kilojoules of heat to its surroundings, while the surroundings do 44 kilojoules of work on the system. So in this one, you have to determine the signs for Q and W. So if the system is releasing heat, we have a negative Q. So Q is going to be equal to negative 66.2. And the surroundings are doing work on the system, so we're going to have a positive W, so positive 44 kilojoules. And when we plug those in for delta E, we get negative 66.2 plus 44 kilojoules. And so delta E is going to be equal to negative 22.2 kilojoules. Okay, finally, in question number 3, the system absorbs 7.25 kilojoules of heat from the surroundings. So the system is absorbing heat, so we're going to have a positive Q of 7.25 kilojoules. Well, its volume remains constant, and we're assuming that only PV work can be done, or pressure volume work. So work, remember, is equal to pressure times the change in volume. Well, if the volume is not changing, that equals 0, so the work is just equal to 0. So when we plug in for delta E, we get 7.25 kilojoules plus 0, and so our total change in energy is just going to be 7.25 kilojoules. The next example involves pressure volume work. So a certain gas expands in volume from 2 liters to 6 liters at constant temperature. Calculate the work done by the gas if it expands A against a vacuum and B against a constant pressure of 1.2 atmospheres. So remember, work is equal to pressure times the change in volume. And so if we're expanding against a vacuum, there is no pressure. So P will just be equal to 0. So work will be equal to negative 0 times the change in volume, so 6 liters minus 2 liters. And so the work done will be 0. If we're expanding against a constant pressure, however, again, work equals negative P delta V. And so our pressure is going to be negative 1.2 atmospheres times V, 6 liters minus 2 liters, which is really just 4 liters. So that gives us a work of negative 4.8. So why is the work negative? Well, work is being done by the system on the surroundings. So remember, when work is being done by the system on the surroundings, W is always negative. So you can tell that your answer is correct. Here's one final example. The work done when a gas is compressed in a cylinder is 462 joules. During this process, there is a transfer of 128 joules from the gas to the surroundings. Calculate the energy change for this process. So, since we're compressing, the work is being done on the gas. So W is going to be positive. Heat is being released from the gas to the surroundings. So our Q is going to be negative. So again, when we plug in, our Q will be negative 128 joules. Our work will be positive 462 joules. Our total energy will be 334 joules, our total energy change. So the energy of the gas is increased by 334 joules. The last thing we need to talk about in this lesson is something called enthalpy, which has the symbol H and is the heat content of a substance. So if we find delta H, or the change in enthalpy, we are finding the enthalpy of a reaction. So this is the enthalpy change that accompanies a reaction, or the heat change, the heat content change that accompanies a reaction. For example, here we have hydrogen gas plus oxygen gas forming water, and the change in enthalpy for this reaction is negative 483.6 kilojoules. Now, anytime that you have a chemical reaction with its enthalpy change listed next to it, you have a thermochemical equation. So you have the equation, and you also have the thermodynamic change that is associated with that equation. So to find change in enthalpy, you have to know the enthalpy of the products, and you have to know the enthalpy of the reactants. So you have your final enthalpy minus your initial enthalpy to get your change in enthalpy. If you have an exothermic reaction, you have a system that is losing heat. Heat is exiting the system. And most chemical reactions are actually exothermic. And two examples would be combustion, which is highly exothermic, right? It's losing a ton of heat, and neutralization. So in an exothermic reaction, the system is losing heat to the surroundings. So it's transferring its heat to the surroundings. And here's an example. Again, the reaction of hydrogen plus oxygen to make water is also going to produce a lot of energy. So energy is a product. When energy is a product, it's exiting the system, and so it's exothermic. In an exothermic reaction, here's another example, a combustion of methane. So methane with oxygen is making carbon dioxide and water. Remember, combustion reactions are really, really exothermic. It creates a lot of energy. And our delta H is going to be negative. So for exothermic reactions, our delta H is negative. Endothermic reactions are the opposite. So in an endothermic reaction, the system is gaining heat, or heat is entering the system, entering endo. So the energy is being transferred from the surroundings to the system. And as the energy increases, the delta H is positive. So here's an example. Carbon dioxide plus water can combine to form sugar and oxygen. In this reaction, heat is entering the system, and so our delta H will be positive 2,802.5 kilojoules for every mole of sugar that's formed. And so we write energy as a reactant in an endothermic process because it is entering the reaction. So here's another example. We have mercury 2 oxide dissociating, or not dissociating, decomposing into mercury and oxygen. And in order to get this process to occur, we have to add energy. So energy is a reactant because it's entering the system. Lastly, we have to draw what are called enthalpy diagrams. So if we have an exothermic reaction, we start with our reactants, and we know that exothermic means that it loses energy. So remember, all reactions take a little bit of energy to start. So you draw, this is the potential energy over here. You draw this curve, it has to overcome that activation energy. But then the products are much lower in energy than what we started with, because remember, in an exothermic reaction, we're losing energy. So if you look at delta H, right, this is where we started, our enthalpy of the reactants and our enthalpy of the products. If you subtract the products minus the reactants, you'll get a negative delta H because the products are a smaller number than the reactants. So again, this delta H for an exothermic reaction is negative. In an enthalpy diagram for an endothermic reaction, again, we start with reactants of some potential energy, and we have to go over this hill, this activation energy, to get to the products. But as you can see, in an endothermic reaction, remember, energy is entering, so our products have a higher enthalpy than what we started with. And you'll see that this delta H, the difference between the products minus the reactants, will be positive, because the products are a bigger number than the reactants.